I just want to touch on what the magnetic field is actually doing, what the magnetic field is really doing inside the conductor or inside our mass. The Dirac sea is something that many people will be familiar with. The Dirac sea is basically all the charged and uncharged particles in whether it be in a mass or whether it be in free space. The Dirac sea is the magnetic fields of all the small particles, what's called the magnetic moments, most of the time cancelling because of uneven distribution of the spin directions. Again, this is called the magnetic moment of a particle. Any particle that has a magnetic moment will have, first of all, spin, and second, charge. There will always be a charge to the magnetic moment as there will be a spin. In this picture we can see there's a spin up and a spin down. Spin up is considered as the positive one half, spin down is considered as the negative one half. So we can see the magnetic moments, they each have a magnetic moment, but one spin up and one spin down, which is quite significant. The energy state in spin down is generally higher than the energy state of a spin up particle. You can see here that any particle that has a magnetic moment, that has spin, that has a charge associated with it, will obviously follow any external magnetic field. They either line up in parallel or anti-parallel with an applied magnetic field. And according to theory, that the magnetic field, the stronger it is, the more spin particles will align. This alignment of particles is generally considered to be the magnetic susceptibility, and different materials will have different susceptibility depending on their hardness, if you like, which is the hardness is the coercive force. So the question is, what evidence do we have for any alignment or anti-alignment? It turns out there's actually tons of evidence, and I want to play a few short video clips, and hopefully this will help.
If you take, let's say, a human being and put him in one of these big, very homogeneous magnetic field magnets, then there's a tendency of that magnetic field to line up the magnetic moments of the nuclei, the spin of the nuclei in the hydrogen in your body, which is in your muscle and in your blood. Now put on a radio frequency pulse, say 60 megahertz or something like that. Then you can make this magnetization of your hydrogen nuclei, you can turn it 90 degrees away from the direction of the magnetic field. Your magnetic moment will precess. If you have coils around, pickup coils, it will induce a signal. If I want to see where the signal is coming from in your body, I put on another magnetic field on top of the very homogeneous one that's called a magnetic field gradient. By that I mean it makes the field stronger in one place and weaker in another place. What you do in order to actually get the image that you want, the fine resolution that you need, is you put on magnetic field gradients of different strengths, a series of pulses. That's why if you get an MRI machine, you hear boom, boom, boom. It's all these pulses that we're putting on with different strengths of magnetic field, perhaps even different directions, because we want to get a three-dimensional picture of you. You record all of these data, and when you finish, you can now use what's called Fourier transform. It's a mathematical technique. You can work back to how strong the signal was in each of these voxels. And so this is how the image is developed.
And a very easy demonstration of the same thing, of alignment of domains and atoms, is also seen in the Barkhausen effect. The Barkhausen effect can be easily demonstrated on the bench and I want to play a short video of this as well. I think it's very important.
Hi, this is the Barkhausen effect demonstration. What we have here is a coil inside the shielded box. This is the coil, which is connected through a BNC cable to an audio amplifier that most of you are familiar with. It's a Unilab audio amplifier for the microwave experiment. I'll close back the coil inside the box. Just check if it's in center. Okay. Now what we have here is a bar magnet that can rotate and can also move forward and backward on an optical table. Here we have the samples. Each sample is inside a rubber cork, and I put the first one, which is soft iron, 0.8 millimeters, and I'll move forward with the magnet, with one pole of the magnet. Now rotate to the other pole. You can hear it. I'll put another sample, which is also soft iron, a little bit thicker, 2 millimeters, and I'll repeat this demonstration. Okay. What I want you to pay attention is, if I'll repeat this movement of the magnet again and again, I still hear the hiss noise. It's the same pole. Okay. Now I'll go to the steel, hard steel, 0.2 millimeter thick. And I'll rotate the pole. Another one, another example of also hard steel, 1 millimeter thick. And the other pole. Now I'll repeat with the same pole again and again, and now I don't hear the hiss. The last sample is a copper 1 millimeter. And we all cannot hear nothing at all.
So we can see here the Lorentz force, where the angle of B is the north pole of a magnet facing out. The velocity V is the direction of travel of the magnetic field, and F is the force exerted on charged particles. We can see now the Lorentz force is exerting a force on all the charged particles inside the wire itself. It lines up the particles, puts a force on them, and free electrons will move with that force. There's also another thing to be considered is electron orbital hopping, which is also another area that could also be considered as freeing electrons from their upper orbitals and orbital hopping across to the next one, to the next one, to the next one. So the charge in a coil conductor, when a magnetic field cuts it at right angles with velocity v does put the force F on the charged particles in the conductor and separates the charges as a result.